بسم الله الرحمن الرحيم. الحمد لله رب العالمين والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is chapter 6, Applications of Integration, and section 6.1 is about area between curves. In chapter 5, we defined and calculated areas of regions that lie under the graphs of functions. So we have seen that integral f of x means the area below the graph of f from A to B. Now we will talk about area of regions that lie between the graphs of two functions. So we will start by integrating with respect to x. Here we have this area between the two functions f of x and g of x, and there is one condition: f of x is always above g of x. So f of x is always greater than g of x. If this is the case, if f of x is greater than or equal to g of x in all the region from A to B, then we need to find the area of the region S. Well, to find the region of the area of the region S, we may divide uh, this region into rectangles, as we did. We divide this into n strips of equal width, and then we approximate each ith strip by a rectangle. The base of the rectangle is called delta x, the width of the rectangle. The height of the rectangle in this case would be f of xi, which is the red one, minus g of xi, because f of xi is greater than g of xi. So that would be the height of the rectangle. F of xi from here to here minus g of xi. So we can write the Riemann sum like this. This is the summation of the n rectangles. This is the height of each rectangle, and this is the width of each rectangle. Of course, the width is b minus a over n as usual. So this, if we take the number of rectangles to infinity, we will get the area between the two curves. So this is the definition of the area between the two curves. If we remember, this is exactly an indefinite, a definite integral, sorry, a definite integral written like this. So the area would be integral from a to b f of x minus gx. This is what we studied in chapter 5. This area written as a limit of sum is exactly the definite integral. We can write it in this notation. So the area between the two curves would be the integral from a to b f of x minus g of x dx. To solve exercises or examples, here find the area of the region bounded above. He told us that it's bounded above by y equals to ex and bounded below but by y equals x and bounded on the sides by x0 and x1. From 0 to 1, so this is from 0 to 1, e to the power x at 0 is 1, and we know the graph of e to the power x. And at 1 it is e, so 2.7, about 2.7. So this is the graph of e of x from 0 to 1. And y equals x, this is a straight line. At 0 it is 0, at 1 it is 1. So this is the straight line, y equals x. So we need the area. Sorry, there is a mistake in the graph. This point is not 1, this is 2.7, so 1 and 1 This is 1 and 1, and this is 0, 0. So this is the equation of the line y equals x, because at 1 it is 1, and this is 1, and this is 1. So now we need to find the area of this region. Well, we draw always, let us draw a rectangle, one rectangle between in this region. We call it typical rectangle. A typical rectangle would be a rectangle like this. The width is delta x, and the height is this function, which is ex, this one, minus the function below, which is x. So this would be the height of the rectangle. So the area between the two curves would be integral from 0 to 1 on the x-axis. So dx is from 0 to 1, and the height of the rectangle, which is ex minus x, this is of f of x minus g of x dx. And that's it. We find the integral. So the integral of ex is ex. The integral of x is x squared over 2 from 0 to 1. So we will have e to the power 1, which is e, minus 1 over 2, minus e to the power 0, which is 1, minus 0. So the answer would be e minus half minus 1. So it's e minus 3 over 2. This is the area between the two curves. Find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. Now I don't have any idea about the region, which graph is up, which graph is below. So I need to sketch the graph. Well, y equals x squared is easy. It is the usual parabola, the vertical parabola that passes by this point. So this is the parabola x squared, and this is also a parabola because it's y equals negative x squared plus 2x. So this is also a parabola because we know that the graph of the quadratic function ax squared plus bx plus c is always a parabola. If a is positive, it opens upward. If a is negative, it opens downward. Here a is negative, here a is negative 1, and b is 2. We know also how to find, so this parabola opens downward. To find the vertex of the parabola, h is negative b over 2a. b is 2, so it's negative 2. A is negative 1, so 2 times negative 1 is negative 2. So h is 1. To find k, we replace x by 1, so it's negative 1 plus 2, that's 1. So the vertex is 1, 1. So if this is 1, so the vertex of this parabola is 1, 1, 1, and it goes downward, it opens downward. Also, for this parabola, to find the x-intercepts, if you put y0 and take x as a common factor, so the x-intercepts are 0 and 2. So this is one x-intercept, and this is the second one. So this is the graph of this parabola, and this is the graph of the other parabola. We can see from the graph that this is the region between them. the region enclosed by these two parabolas, this region. But also you can find these intersection points algebraically. You can, this is y equals x squared, and this is y equals 2x minus x squared. So if you put this equation, this y equals to this y, you will get the intersection points. If you take x squared to the other side, I have 2x squared. If you take 2x also to the other side, I will have negative 2x. Now, if you take 2x as a common factor, I'll have x minus 2. So either x is 0 or x is 2. Now, if x is 0, you can replace x 0 here or here. So this is one intersection point. And if x is 2, another point of intersection, 2 to the power 2 is 4. Sorry, there is a mistake here because if you take 2x as a common factor, you have x minus 1. So this is not 2, it's 1. So if x is 1, y would be 1 square, which is 1. So these are the two intersection points, 0, 0, 1, 1. Now, to find the area, I need a typical rectangle. This is a typical rectangle. If you move this rectangle right and left, always the width of the rectangle would be delta x. And the length of the rectangle would be this parabola, which is 2x minus x squared minus the parabola below, which is x squared. So this is f of x minus g of x, or y1 minus y2, for example, or y up minus y lower. So the integral, or the area between the two curves, this area now, would be the integral from x-axis, x from where to where, x from 0 to 1, the length of the rectangle, which is 2x minus x squared minus x squared, that's minus 2x squared dx. So this integral will give you the area of this region. Well, this is 2x squared over 2, and this is x cubed over 3. It would be x squared from 0 to 1 minus 2 over 3x cubed from 0 to 1. So this would be 1 minus 0, which is 1. And this would be 2 over 3 times 1 minus 0, which is 1. So 1 minus 2 over 3, that's 1 over 3. So the area of this region is 1 over 3. Now the case is not always like this. Here, always one curve is above the other curve in all the interval. But sometimes we have something like this. So sometimes f of x is above g of x, and in another area g of x is above f of x. So in this case, the area would be integral of absolute value of f of x minus g of x. So whenever f of x is greater than g of x, the absolute value would be f of x minus g of x. But if g of x is greater than f of x, we take g of x minus f of x. So if in the interval from a to b, the curves intersect inside the region, then we will have three areas like this. We have to find a1 plus a2 plus a3, or as many regions as we have. So for example here, find the area of the region enclosed by the curves sine x and cosine x from 0 to pi over 2. You need to sketch the graph to understand the situation. So at 0, sine 0 is 0, cosine 0 is 1. Pi over 2, sine pi over 2 is 1. So the graph of sine goes like this. And cosine pi over 2 is 0. So the graph of cosine goes like this. This point of intersection is pi over 4. Sine pi over 4 equals to cosine pi over 4 equals to, if you use the calculator, square root of 2 over 2. Okay, and square root of 2 over 2 is a number between uh, 0 and 1. It is 0.71, okay, approximately 0.71. So this is 0.71. So now from 0 to pi over 2, I have from 0 to pi over 2, I have two areas enclosed by the curves. I have this area and this area. Enclosed means between the two curves. So I can say this is S1 and this is S2. If I take a typical rectangle here, the graph of cosine would be above the graph of sine. While in this region, the graph of sine is above the graph of cosine. So I will have to consider these two cases. So the area between the two curves would be, for the first region, I go from 0 to pi over 4. The length of the rectangle is cosine minus sine. In this region, plus from pi over 4 to pi over 2. In this region, the length of the rectangle is given by sine x minus cosine x, and the width is dx. So you find that these two definite integrals, and you will get the area of the region bounded by the two curves. So the integral of cosine is negative sine. Sorry, the integral of cosine is sine because the derivative of sine is cosine. So sine x minus the integral of sine is negative cosine from 0 to pi over 4. Integral of sine is negative cosine. Integral of cosine is sine from pi over 4 to pi over 2. So we will have sine pi over 4, which is square root of 2 over 2, plus cosine pi over 4, which is square root of 2 over 2, minus sine 0, which is 0, plus cosine 0, which is 1. Here, I can take the negative sign out if I like. because I have negative negative. So I'll have cosine x, cosine pi over 2 is 0, plus sine pi over 2, which is 1, minus cosine pi over 4, which is square root of 2 over 2, plus sine pi over 4, which is square root of 2 over 2. So I have here, if you add these two, you get 2 square root of 2 over 2, which is square root of 2, minus 1, and this is minus 1, and plus square root of 2. So the answer would be 2 square root of 2 minus 2. This would be the area between cosine and sine in this interval. Now also, it is not always the area one of the functions is above the other. Sometimes we have one of the functions is written to the right of the other, or let us say one of the graphs, because this may not be a function. So one of the graphs is to the right of the other. So in this case, the typical rectangle would be horizontal like this. The width of the rectangle would be delta y because this is part of y. And the length of the rectangle in this case would be f of y minus gy, the one to the right minus the one to the left. And in this case, we have to solve the equations for x. So x equals. And this would be the area. So we will have x equals f of y, x equals g of y, and y from c to d. Okay. So the integral here would be in terms of y, delta y with respect to y, and y runs from c to d, and we have f of y to the right minus g of y to the left. So according to the graph, you determine which one to use. Do you integrate with respect to x or with respect to y? Let us sketch the graph here and see. We have y equals x minus 1. This is a straight line. And y square equals 2x plus x. We have y square and x to the power 1. So this is in fact a parabola, but a horizontal parabola. You know the graph of x equals ay square plus by plus c. This is always a horizontal parabola. If a is positive, it opens to the right. If a is negative, it opens to the left. I can find the vertex k here would be negative b over 2a, and h, I replace y by k to find h. So the vertex would be hk. Okay, this is how we get the variable, the vertex in this case. So for example, to graph this parabola, I will solve it for x to write it in this form. So 2x is equal to y square minus 6, or x equals half y square minus 6 over 2, which is minus 3. So this is the parabola. Now a is half, so it opens to the right. B is 0 because b is the coefficient of y and there is no y here. So k would be negative b, which is 0. So over anything 0, so k is 0. Now to find h, I replace y by 0. So half times 0 is 0 minus 3, negative 3. So the vertex of this parabola is negative 3 and 0. Now to graph the parabola, 1, 2, 3, this is negative 3 and 0, and the parabola opens to the right. And this is the line y equals x minus 1. But to find the intersection points between the line and the parabola, we need to equate the two equations. Let us solve this also for x. So x would be y plus 1. So I have x equals y plus 1 and x equals half y squared minus 3. So I say y plus 1 equals half y squared minus 3 to find the intersection points. I can multiply by 2 to get rid of the denominator. 2y plus 2, here y squared minus 6 because you multiplied every term by 2. Then I have y squared minus 2y minus 6 minus 2 is minus 8 equals to 0. If you factor this, y minus 4 times y plus 2 is 0. Negative 8 and negative 2y the second term. So either y is 4 or y is negative 2. So y negative 2 and y is 4, they will intersect here and here. Well, if y is negative 2, x would be negative 2 plus 1, negative 1. So a negative 1 and negative 2, this is a point of intersection between the two graphs. And if y is 4, x is 4 plus 1, which is 5. You can find x from here or from here. So 5, 4, this is another point of intersection. So this line should pass between these 2 points, and also the parabola should pass between these 2 points. And this is now the region. We need to find its area. Now, if you try to use a typical rectangle which is vertical, in this area, this curve is above the line. But if you move the rectangle to the right, in this area, the curves changes. And now this curve is above this curve and the line is not there. So if you want to find the area of this region using a vertical rectangle, which means you will integrate with respect to x, you have to divide this region into 2 regions. And you find area of region 1 plus area of region 2. But if you consider a horizontal rectangle, a typical horizontal rectangle like this, and you move this rectangle up and down, anywhere, this rectangle would be always the curve to the right is the straight line, to the left, this parabola. But now the width of the rectangle is delta y. And the length of the rectangle would be the line, which is y plus 1, x equals y plus 1, minus the parabola, which is x equals half y squared minus 3. So now you can solve this area. You can find this area using one rectangle, but you will integrate with respect to y. So y runs from negative 2 to 4. So these are the limits of the integral. And the length of the rectangle would be y plus 1 minus half y squared minus 3. And the integral is with respect to y. And now you continue and find the area. So I will write it from negative 2 to 4. I have y plus 1. 1 minus 3 would be 1 plus 3, which is 4, and minus half y squared after expanding. So the integral of y is y squared over 2. The integral from -2 to 4. The integral of 4 is 4y from -2 to 4. And negative half y cubed over 3 from -2 to 4. So I will have half times 4 square, which is 16, minus -2 square is 4, plus 4 times y, replace it by 4, minus, replace it by -2, so it would be plus 2, minus 1 over 2 times 1 over 3 is 1 over 6, and I have 4 to the power 3 minus -2 to the power 3 will give you -8, so I'll have positive 8, and you just use the calculator and find the answer. So here I will have 12 over 2, which is 6, and here 4 plus 2 is 6 times 4, this is 24, and 4 to the power 3 plus 8, this is 72, divided by 6 is 12. So 24 minus 12 is 12, plus 6 is 18, and the area is 18 square units. Please study the section again and again to understand carefully how to find the area between two curves.